Welcome, sir.
It's coming now. Okay.
Good evening, sir.
Good evening, everyone. So, welcome to day 3 of our ATAL sponsored FDP on innovative green energy generation and storage technologies. I hope you found yesterday's sessions interesting and are ready for today's exciting topics. Yesterday, Professor Srikanth emphasized the importance of understanding the philosophy of green energy and highlighted the ground level problems associated with the various green energy technologies. Later, Dr. Sarvottam Jyoti discussed about the need for innovation in the renewable energy sector to remain competitive and sustainable. So we have two interesting sessions planned for today. The first session will focus on advancements in energy storage technologies. The speaker for this session is Professor K.R. Balasubramanian, Department of Mechanical Engineering, NIT, Tiruchirappalli, an expert in energy storage and renewable energy systems. Professor Balasubramanian will share valuable insights into the advanced energy storage systems. In the second session, Dr. Sridhar, Research and Development Manager at Amarraja Energy and Mobility Limited, will talk about advanced materials, components, and management strategies for lead-acid batteries. I encourage everyone to participate actively, interact with experts, and share your thoughts during the sessions. Let's begin our first session with a warm welcome to Professor Balasubramanian. He will be sharing his expertise and perspectives on energy storage systems. It's a privilege to have such a distinguished expert with us today to enrich our understanding of the crucial field. Before we begin, I invite our session coordinator, Dr. K. Ravikumar, to introduce today's speaker. Over to you, Dr. Ravikumar, to share more about our distinguished speaker. Thank you.
Thank you, sir. Good evening, everyone. It is my great pleasure to introduce today's distinguished guest, Dr. K.R. Balasubramanian, sir, a highly respected academic and researcher in the field of mechanical engineering. Dr. Balasubramanian, sir, serves as a professor in the Department of Mechanical Engineering at the esteemed National Institute of Technology, Tiruchirappalli, India. Dr. Balasubramanian, sir, is a well-known researcher and academician whose expertise spans diverse areas such as renewable energy systems, solar thermal systems, ergonomics, welding, and coatings. He has made a significant mark in his field with over 132 publications in international journals and conferences, alongside several book chapters that further enrich the academic disclosure. Throughout his career, Dr. Balasubramanian sir has presented his research at numerous national and international conferences, sharing his knowledge and insights with the global academic community. His editorial and reviewer roles in the reputed peer-reviewed journals reflects his commitment to maintaining the highest standards in the research. In addition to his academic contribution, Dr. Balasubramanian sir has successfully managed various international and national funded projects, showcasing his leadership in the applying research to real-world challenges. He has also mentored numerous PhD and MTech students, fostering a culture of innovation and excels among emerging researchers. Dr. Balasubramanian sir influences extends to professionals and academic circles where he actively participates in international memberships and serves as an external examiner for PhD and MTech Viva Voice examination. His dedication to advancing engineering knowledge and education is truly commendable. We are truly privileged to have such a distinguished expert with us today. Dr. Balasubramanian sir insights are sure to offer valuable perspectives that will inspire us and enrich our learning journey. I am delighted to share that I have successfully completed my PhD under his esteemed guidance. I feel truly fortunate and honored to have been his student. Thank you, sir. Please join me in giving a warm welcome to Dr. K. Balasubramanian, sir. Thank you, sir. Please share your thoughts, sir.
Is it visible?
Yes, sir. Yes, sir.
Okay. Shall I start?
Yes, sir. Please continue,
Sir.
sir.
Very warm good evening to one and all. I am delighted to make this presentation today in this ATAL FDP program. Congratulations to the Institute for organizing a wonderful topic on this energy storage technology. In this session, I am going to discuss about the various energy storage technologies. And I will give some insights about what in our laboratory we are working on. Okay, our research team is working on about the energy storage technologies. Thank you, Ravi, for giving a detailed introduction about me. And now everyone know that the world is witnessing climatic change, and everywhere there is unpredicted rainfall, and there is no even rain at some places. So these are all most challenging for us, for the future generation also. So this is the time one has to wake up and think about what is the possible way of reducing the greenhouse gases. So we need to use the energy in a judicial manner, and also as much as possible we need to try to store the energy and use it whenever it is required, right? So among the energy that is available, right? So different forms of energy is available. Among the different forms of energy, right? Solar energy, which is considered as the most promising form of renewable energy, right? And the advantage being it is readily available, right? Regenerative and also pollution free. Okay, and this can be obtained throughout the year. Right? The only problem is that it is of about the uneven distribution. The solar radiation is of uneven distribution. So what we can do is we can incorporate the solar thermal systems, right, for storing the heat energy, and that can be used whenever it is needed, right? So that will help us to temporarily mismatch between the supply as well as the demand. And basically, if you see the thermal energy storing technologies, right, basically there are three kinds. One is the sensible heat storage, the other one is the latent heat storage, and then third one is the thermochemical heat storage. So the factor or the thing that is very important to consider here is about the amount of heat stored. So that depends upon the factors like the mass and the heat capacity of the storage material, right? And the temperature difference between the initial and final state. So these things will decide upon how much of heat that is being stored. So here we can see the three different types of heat storage. So in the first figure, we can see the sensible heat storage, right? Where here molten salt, sand, rock, concrete. So these types of materials are used for storing the heat that is working under in the sensible heat region. Then the second one is the latent heat, right? And here there is a phase change that occurs. That is solid to liquid phase change occurs. So that is the latent heat storage. And here the PCM materials are being used like salts, metals, the organics, okay? And there are some advantages and some disadvantages among these three that we will discuss in detail, right? And the fourth one is the thermochemical, right? And here we can see the heat losses is very less in the thermochemical. And also, if we see the energy storage density, it will be very minimal in the sensible heat storage, and it is almost neutral or in between in the latent heat, and it is more in the thermochemical. Okay. However, the development wise, if you see the thermochemical way of storing the heat is in the development stage, or we can call it as in the research stage. It is not reach the maturity level, right? And the sensible heat storage, it has been used in many places, okay? And the industrial development, if you see, it is maximum in the sensible heat storage method and very minimal in the thermochemical way of heat storage. And here you can see the non-metals like concrete, rock, gravel, right? Even brick, the marble, granite, even sandstone. So those are all the materials that are used for storing the heat. But the problem is the low specific heat capacity and also the thermal conductivity. So that are all the major obstacles, right? Which decides the reliability of the storage. And the metals like even the copper, aluminum, cast iron, pure iron, right? So these along with other alloys are suitable for high temperature storage. But the one thing is that cost wise, it is very higher, right? So that is the another problem in making this in a commercial way. And the third method, that is the chemical thermal energy storage. In this, the energy stored and released is due to the reversible reaction, right? So here, the chemical methods of TCS, TES are classified as sorption storage and thermochemical energy storage. So it comprises the solid to gas or liquid to gas or the gas phase system. So here in this chemical TES, the energy is stored in thermochemical heat storage as a result of dissociation reaction, right? So which is then even recovered in a chemically reversible reaction. So here the thermal cycle consists of charging, storing, and discharging. And here the amount of heat that is stored in thermochemical energy storage involving the solid gas phase depends upon the pressure of the gas, okay? And it also even depends upon the operating temperature and also the reaction enthalpy. So typically the storage density of the latent heat storage medium, right, is higher when we compare with the sensible heat storage medium, because due to high enthalpy change, right, which occurs during the phase transition. However, the thermochemical energy storage has the highest storage density, right, compared with the other two modes, that is the latent heat storage as well as the sensible heat storage medium, right? But the thermochemical energy storage materials are only in the development phase, and no such system is commercially available. So that is the one major thing, but a lot of research is going on. And the commercial viability of the latent heat storage is limited due to the material characteristics, and hence it is in the development phase. However, this sensible heat storage, so that is commercialized in a large manner. And when we discuss about the durability of the sensible heat material is almost around 20 years when we compare with the latent heat sensible material, which is around 1/4 of their lifetime. And when we compare the thermochemical energy storage, it is about 1/10 of the lifetime of the sensible heat storage material. So the lifetime is very less for the thermochemical energy storage, and similarly for the LHS materials. So among these different types of thermal energy storage methods, the latent heat storage has the most flexible operating temperature range, right? Which followed by considerably lower operating temperature ranges for sensible and thermochemical energy storage. So here we can see the classification of the thermal energy storage system. So here we can classify into two basic classifications. One is the physical storage, the other one is the chemical form storage. And the physical storage, once again, it can be classified as sensible heat storage, and the next one is the latent heat storage. And in the sensible heat storage can be stored in the solid or the liquid form. And in the solid, the candidates are the non-metals like rocks, even metals and alloys are used. And under liquid, the molten salts, the water, that is one of the best example, and thermal oils. So these are all the liquid-based SHS storage mediums. And in LHS, PCMs are majorly used for conversion of solid to gas, solid to liquid, liquid to gas, and solid to solid. So here we can see the different types of PCMs, like organic PCMs, inorganic PCMs, and eutectic PCMs. And here the examples of organic PCMs are paraffins, fatty acids, esters, alcohols. Okay, so these are all people are using. And the inorganic PCMs are the salts, salt hydrates, metallic compounds, metal alloys. Okay, and the binary, that is the eutectic PCMs. So that is the mixture, that is organic, and inorganic, and even organic, inorganic. So these are all the other eutectic based PCMs that are being used. And the solid to solid, that is the polymer based. So here we can say these are all under majorly in the research based, right? And the thermochemical energy storage, the two methodologies, one is the sorption type, the other one is the chemical reaction type. So the hydride systems, carbonate systems, hydroxide system, right? So these are all solid to gas, the type of system. And ammonia system, that is liquid to gas, and organic system, gas phase. So these are all the different thermal energy storage systems. So here the heat of phase transition in the solid to solid PCMs is relatively less when we compare to the solid liquid PCM. So majority of the PCM considered for the TEs are solid to liquid phase transition materials, right? And also these are all sorted on the basis of the nature of materials, like whether it is organic, inorganic, and eutectic, right? And these PCMs are further categorized on basis of their phase transition temperature as low, medium, or intermediate, and high. Okay, so in the case of low, the melting points will be less than 220 degrees centigrade, And in the intermediate, it ranges between 220 to 420 degrees centigrade. And in the high temperature range, it is more than 420 degree centigrade, right? And the organic PCMs, like the paraffin wax, alkanes, esters, fatty acids, right? Alcohols, and even the other components, including the ketones, amides, sugars, right? And oleochemical carbonates. So these are all being used, right? So these are all the organic PCM. And the inorganic PCMs are the salt hydrates, metals, right? And the other metallic salts like carbonates, chlorides, right? So these are all some of the appropriate PCMs like magnesium chloride, hexahydrate, sodium sulfate, decahydrate. So people are trying by modifying certain percentage among these things, and they are identifying how best the energy can be stored. The specially engineered materials having a desired thermophysical properties are designed with a mixture of components of the eutectic point, right, which are derived from the phase diagram and are known as the eutectic PCMs, like organic, inorganic, like that. Okay. So the eutectic PCMs may consist of the eutectic mixture of multiple materials, like as I mentioned, the organic components, inorganic components are mixture, right? And here we can see in this figure the durability, right? For sensible based one, the latent heat and chemical way, right? So the durability in terms of years is maximum for sensible heat storage materials, and it is lesser for latent heat storage materials, and further it is lesser for chemical based energy storage materials. And the commercial viability we can see here, the sensible heat storage materials are commercially available, whereas in the sense that this latent heat, it is commercially available for certain materials, not for all the materials. However, in the chemical heat storage, it is basically in the research phase and not at commercially available. And here we can see the temperature, and in the left hand side, the y-axis, and the storage density on the right hand side in the y-axis. In the x-axis, we can see the sensible PCM, latent heat based and chemical based storage, right? So the storage density is very less for sensible heat storage materials. However, for chemical based storage, it is having maximum storage density, and it is intermediate for latent heat storage medium. And the only problem is this is in the research stage, not at completely matured. And here we can see the organic PCM materials and the inorganic PCM materials. So in the x-axis, we can see the latent heat, and y-axis, it is energy density. So the different heat storage materials are shown here, starting from polyglycol E400, dimethyl sulfoxide, polyglycol, paraffin, right? And the other formic acid, benzamide, acetic acid, and so on. So from this figure, we can understand that the component, the material, that is the erythritol, right? It has the maximum energy density, which is more than 400. And the latent heat is also comparatively higher than other materials. This will be around 330 or 340, something like that, right? So then next to that, we can see here the formic acid and other materials, right? And on the right hand side, we can see the inorganic PCM, right? And MgCl2 6H2O, right? And among this, we can see the materials like NaCl, okay, and aluminium, okay, and the KF. So these are all the materials which has very high energy density, that is around 1000. So one can compare the organic PCM and the inorganic PCM. So the inorganic PCM is almost 2.5 times more than the organic PCM. And the latent heat is also a little bit higher compared to the organic PCM, which is more than 450 and nearing to 500 kilojoule per kilogram. And here we can see some advantages and some disadvantages of the organic PCM, right? So the advantages, it will freeze without much supercooling or subcooling. So that is one major advantage, and it can be incorporated directly. And the thermal performance is also better, and it is compatible with other conventional materials of construction. And there is no problem with this segregation. There is no segregation, and chemically stable, and high heat fusion. So that is another important thing, and also safe and non-reactive. Okay, so that is very major important thing. And the other one is the recyclable. Okay, so these are all the advantages of the organic PCM, and some disadvantages. If you see, the thermal conductivity is very less, right? And sometimes even it will burn easily, and the phase change enthalpy and density is low, and it needs large surface area, and high heat transfer rates are required during the freezing cycle, right? And is also have low heat capacity. Okay, so these are all some of the disadvantages of the organic PCM. Now coming to the inorganic PCM, this possesses high thermal conductivity, right? Large heat storage capacity and lower volumetric expansion. Okay, so that means it occupies less space and high heat of fusion per unit volume. And it is not that much costly when we compare with other PCM materials. And the other important thing is also, it is also a recyclable. Okay, and the phase change enthalpy is higher. The disadvantages of this inorganic PCM, it needs high degree of supercooling. Okay, and the thermal stability is another big problem. And here the phase segregation will happen. And the another important thing is the corrosiveness. Okay, and it also points to degradation and chemically unstable. It needs container as well as support. So these are all the disadvantages of the inorganic PCM. Now coming to the eutectic PCM, it has sharp melting temperature, okay, and high volumetric thermal storage density, and there won't be any phase segregation, okay, and congruent phase change. Some disadvantages, right? Low total heat capacity. The cost wise, it is very high, okay, and some eutectics needs supercooling effect, okay, and the data, test data about the thermophysical properties of these materials is not completely available. So that is another disadvantages of this eutectic PCM materials. So far we have discussed about the different materials, right? The heat storage materials, thermal storage materials. Now let us discuss about the thermal conductivity enhancement techniques in phase change materials. So researchers are adopting different methodologies in order to increase the energy storage. So among that, there are few enhancements techniques available, so that we are going to discuss now. One is the fin-based, that is the extended surfaces, then encapsulation of the PCM, and addition of nanoparticles in the PCM, then metallic foam, right? And when we come to the addition of nanoparticles, carbon nanotubes, graphene nanoparticles, silver nanoparticles. So these are all being attempted. And in the case of metallic foam, nickel, copper, graphite foams are being tested. So these are all the different thermal conductivity enhancement technique. So some researchers are using 2 or 3 techniques also combinedly to improve the efficiency of the system. So here we can see the different techniques, the addition of nanoparticles like carbon nanotubes, graphene nanotubes, silver nanoparticles, okay? And the metallic foam, nickel foam, copper foam, graphite foam, even the encapsulation, okay? And other materials like hexagonal boron nitride, spongy graphene. So these are all being used. And apart from that, shape stabilized phase change materials are being used. So these are all of porous in structure, so which can absorb the PCM into it and hold it, so which will arrest the leakage and also provide better stability. So that is how this been getting popular. So according to the sizes, it can be classified into macro porous, meso, micro, and hierarchical porous according to the structure, right? Metal foam and hierarchical porous and the carbon nanotubes. So this is the shape stabilized phase change material. Basically, the PCM will be formed initially, and it will be mixed with other materials to form a shell, right? And this shell basically will be a porous in nature, so that will hold the heat which is stored by the PCM. Okay, so here we can see the porous material, right? So, and the PCM in the porous material. So these are all the shape stabilized PCMs. Now coming to the thermal management of the lithium ion battery cells. So nowadays, the even automotive industry is moving towards the electric vehicle, right? So in order to reduce the pollution and also to reduce the consumption of the fossil fuels, right? Like the diesel, petrol, right? The industry is moving towards the e-vehicle. The major problem in the e-vehicle is the battery, right? So the battery thermal management system is very, very important. So here we can see the cooling methodologies that is being adopted. One is active battery thermal management system, which can be done by air cooling, and the other one is liquid cooling. Then passive way of battery thermal management system, that is PCM based one. The other one is the heat pipe based. And in the PCM, even pure PCM is used, and the composite PCM with the carbon composite or metal composite, these are also being tried. Then hybrid battery thermal management system like PCM plus air or liquid or along with the heat pipe. So these are all also being tried. So here we can see in this figure the battery cells. Okay, these are all the PCM material, and here you can see the battery cells that is being inserted. And when the battery generates heat, right? So that will be absorbed by this PCM. Okay, so that will enhance the life of the battery. Okay, the major cost in the e-vehicle goes to the battery. Okay, and this is the another thermal management of lithium-ion battery cells using PCM. So here, so this is a video which shows how the thermal management is being done using the PCM.
This is under new energy company. We are honored to declare that we have developed phase change materials for cooling lithium long battery. Though similar products could be seen in current market, there are enough reasons for ours to stand out to be your better choice. Those using paraffin wax melting.
Ravi, whether it is audible and it is going fine, is there any
Sir, audible,
disturbances?
Audible, sir.
Okay.
For the battery pack usually come with something disturbing. Batteries melt with a possible leak when working under high temperatures. Other products based on PCM and graphite are hard and far from pressure resistant, leading to shorter circuits with favorable electrical conductivity, which is a fatal flaw. We are glad to introduce our products in detail for you. Through injection process, these soft materials can be easily made into all kinds of shapes to fix any type of batteries. We also specially designed a kind of holder for large battery packs with convenient assembly no matter how large they are. There are two types of products we developed. The white one without graphite and the other one with graphite in it, which conducts heat better. Since graphite is electrically conductive, measures were taken to make the products insulated, as we are going to show you. Besides, you don't need to worry about their cooling effect. Exposed at an ambient temperature of 85 Celsius degree for 4 hours, our PCM reached 59 Celsius degree, which proves they can control the temperature well while the batteries are in use, ensuring a longer life and a higher security. Our products have passed partial testing of UN 38.3 safety to be concluded. With quantifiable injection molding process, our PCM are able to extend battery life by 40%, safer and difficult to self-combust. All these adds up to the biggest advantage of PCM.
So these are the advantages of PCM. So this will effectively maintain the battery temperature. So a passive thermal management of the photovoltaic cell, right, using the PCM also helps in improving the overall efficiency of the system. So we know that the photovoltaic system will work effectively in a lower operating temperature. If the temperature rises, the performance of the PV module will goes down, right? And the incorporating of the PV and the PCM is a novel technology in a PV module, and PCM coupled in a single module for the thermal management of the silicon-based PV cells, right? Which ultimately improves the reliability of the system. So here, the PCM is placed in channels under the cells, and during the day, as the temperature increases, right, in the cell, the PCM will capture their heat and it will melt. Then what happens during the night? It transfers the heat to the environment and turns into solid state, right? But the major problem is the cost of the raw materials. So this is the experiment which we conducted in our laboratory, right? So here we can see the photovoltaic panel without PCM and photovoltaic with PCM. So, so here we used the PCM as the back sheet, right, to reduce the surface temperature of the PV cell, right? So the surface operating temperature can be reduced in order to improve the electrical efficiency. So here we can see another
Phase change materials
materials.
cooling is a distinct form of passive conductive cooling. PCM are substances capable of retaining thermal energy, allowing temperature stabilization. These will absorb or release significant quantities of so-called latent heat when these experiences a change in their physical state, such as during the melting and freezing cycle. PCM is listed as organic oil, inorganic salt hydrates, and eutectics. The melting temperature and latent heat are the two elements for the identification of the appropriate PCM. While this cannot be considered as passive cooling in the strict sense, extra effort is not required, and heat dissipated more conductively and has the effect of retaining the same temperature. As a matter of fact, PCM is integrated with the PV module would become a better alternative due to its important properties for daytime heat absorption and nighttime release, such as high latent heat, high absorbing capacity before melting or solidification, the constant temperature during phase transition, slightly higher melting temperature. Salt-based PCMs, for example, may react with metal, causing corrosion, while paraffin may react with plastics. As far as temperature is concerned, it is essential for the PCM to have a melting point above the ambient temperature at which it operates. A melting point temperature below that will trigger the PCM to liquefy before the panel is even heated, rendering it useless. Organic PCMs, such as paraffin, are widely used for thermal storage systems. However, as per various studies, the structure of organic hydrocarbons has a low thermal conductivity, which reduces the heat charging and discharging rate during the melting and solidification cycles. In contrast, inorganic PCMs have a higher phase change enthalpy, resulting in better thermal properties. A specific PCM, CaCl2 6H2O, Fe3Cl2 6H2O eutectic, can be used for control of temperature and cooling of PV panels.
So, how to select the PCM for PV panels, right? So nowadays we know that India is more committed in investing in the PV technology or installing the solar based PV power plants, right? So far, if you see this data, the India's solar power installed capacity is around 92 gigawatt. And in order to achieve the carbon neutrality by 2070, right, we need to use the solar power as much as possible, right? And so we need to, we are committed, right? Already in the Paris Agreement, we have committed that the emissions will be reduced by 30 to 35 percentage, right? And also it will help in achieving the sustainable development goals of the UN nations, right? So our government, Indian government, is actively focusing on the installation of the PV based power plants. And the major thing is this in this is the maintenance, right? And the maintaining the temperature in an operating level. Okay, so how to select the PCM for PV panels? So we need to have some data for that. So how to collect this? So here we can see what are the data collections that are required. One is the solar irradiation. So according to the geographical place, right, we can identify what is the solar irradiance at that particular location and the ambient temperature. Okay, so that has to be find out. Then the PV temperature at that location, and also the seasonal conditions, whether it is a summer or winter. Suppose if the temperature is more than 25 degrees centigrade in the summer, right, then we have to use the PCM. If it is not, no needed. Similarly, in the winter, if the temperature is greater than 25 degrees centigrade, we can use the PCM. Then accordingly, we have to select the PCM, right? Whether the whether it is more, the temperature is very high or less according to the ambient conditions, we can test it. Then we can use the PCM, right? Accordingly, we can find out whether the efficiency of the PV panel is increasing or not. So before finding out the PCM, we need to collect these data, how much of solar irradiations is occurring in that particular location, and the ambient temperature and the PV panel temperature. So accordingly, the PCM has to be selected. So sometimes if you see, the surface temperature of the solar PV panel will increase up to 50 degrees C. So in the Tiruchirappalli climatic zone, right, the temperature is around 50 degrees centigrade for in the solar PV panel, and every degree rise in the temperature of the PV panel will drastically reduce the electrical efficiency. Okay, so if you want to increase the electrical efficiency of the PV panel, the solar PV panel temperature has to be maintained in an optimum level. So how to do that? That can be done by integrating the PCM to PV panel, right? So that will effectively control the surface temperature of the PV panel and also enhance the electrical efficiency. And typically the thermal conductivity of the PCM materials are very poor, and sometimes the leakage also found when it is in the liquid stage. Okay, so due to these issues, the PCM materials are not effectively utilized in the real-time solar PV applications. So our research team, what we have done is we have prepared a novel form-stable PCM material, right? Polyethylene glycol 1000 is used, and we added the expanded graphite material, right? And the experiment was conducted in the real-time atmospheric conditions. So here you can see the experimental setup, which there are three types of panels you can see. One is the bare PV panel, where there is no external cooling, only the air cooling, normal air cooling. The other one, second one, is the PV panel attached with the heat sink. Okay, so that is the one. The third one is PV panel with the heat sink and the PCM. Okay, so here the thermocouples are installed at various locations to find out the temperature at different regions, and it is connected with the data code system, and the infrared temperature gun is used to find out the surface temperature of the PV panel. And using this, we have done the work. The thermal conductivity and form stability of the PCM was significantly improved with the addition of the expanded graphite particles. So here, the acrylic sheet is used both at the top and the bottom. Okay, and here the leakage is arrested with a suitable glue that is used. And here we can see at the bottom, the thermocouples are fixed, and also in the heat sink, and also on the top surface also. So here we can see the temperature variation with respect to time from 11:30 to 3 p.m., 11:30 a.m. to 3 p.m. So the variation in the temperature for bare PV panel ranges from 33 degrees centigrade to 47 degrees centigrade. Okay, and the heat sink and the PV panel, it ranges from 31 to 37, nearer to that. And when we employ the heat sink with PCM in the PV panel, right, the temperature between 30 and 36 or 37. Okay, so in that range it occurred. So there is, we can see a good reduction in the surface temperature. Even 1 degree reduction of the surface temperature will improve the electrical efficiency of the solar PV panel. So here we can see in the right hand side the overall electrical efficiency of the bare PV panel, heat sink with the PV panel, and heat sink plus PCM adapted in the PV panel. So for bare PV panel, the electrical efficiency is around 10%. For including the heat sink at the bottom of the PV panel, another 1 degree rise we observe. And when we adopt the heat sink along with PCM, a further incremental of about 2% is observed. So totally around 3% of electrical efficiency we achieved with the use of the heat sink and PCM. So from the experimentation, these are all the findings. So the temperature difference between the bare PV panel and the panel plus heat sink combination exhibits high temperature difference compared to the panel plus heat sink assembly. That is around 11.35 degrees centigrade, right? And due to the reduction of surface temperature of the PV panel, the overall electrical efficiency is enhanced. And here we used the aluminum heat sink. This has an improvement of 1.072%, whereas in the combined heat sink with the proposed composite PCM, it further improved up to 3.667%. The next application is on solar stills. So we know the working principle of the solar still. Okay, so here there will be a top cover, and in the basin the raw water will be filled, and in the bottom the paint, black paint, will be coated. Okay, and once the solar radiation is instant on the water, okay, through the transparent cover, the water will be evaporated and it will get deposited on the transparent cover and it will get condensed. The water droplets will form, and if more water droplets form, it comes through this top cover as it is inclined. Okay, due to gravity, it will come and it will be collected. Okay, so in order to improve the efficiency of the PCM for solar stills, right? The PCMs are being used. Okay, so that will increase the generation of the water. Okay, more generation of water. So here in this right hand side, you can see the frame, wooden frame, over which there is an insulation to avoid the heat loss, and there is a PCM, okay, over which it is coated. Okay, so that enhances, that will store the heat and it will give additional to the water, that will increase the evaporation and the water generation will be enhanced. So in this graph, we can see the conventional solar still, that is the second curve at the bottom, and over the top you can see the solar still with incorporating the PCM. So the productivity is enhanced here. So between 6 to 4, okay, we can see how it drastically increases productivity between 11 and 3 p.m. Okay, and drastically it reduces after 3 p.m. Before 11 also, the productivity is less. Once again, we can see here, after 3 p.m., once again, there is a incremental in the productivity. up to 6, 7, 8. Okay, then it decreases. So the additional incremental in the productivity can be obtained with the use of the PCM. Next one is the use of PCM in the cold storage systems. So there are a wide range of applications such as air conditioning, right? Free cooling of buildings, food storage, medical, cold packing, right? So in these areas, PCMs are used for maintaining the temperature, right? That is the another important thing. So in the cold storage applications for storing the food products, or in the medical applications for storage of the blood samples. Okay, so there these PCMs are majorly used. So even in the refrigerated vehicles, right? So large amount of fuel is used for providing the cooling inside the vehicles. So in that areas, the PCM material can be fixed. Okay, so that will maintain the temperature for a longer period, and also this refrigeration pads can also be the PCM pads can be used in the refrigerated vehicles. Okay, so that's how the use of the fuels can be reduced drastically. So here you can see
PCM, or phase change material, is capable of quickly storing large amounts of cooling capacity and releasing it over a longer period of time. When PCM is activated and has stored its maximum amount of energy, it turns solid. When it releases its cooling energy, it becomes liquid again. Easy cool-down PCM packs can be reactivated over and over again by simply placing them in a fridge or freezer. Applied in a vest, PCM can help you maintain a safe body temperature and prevent overheating and heat stress. PCM cooling vests and other apparel can be worn under clothing and don't need airflow to function like evaporation vests do. PCM vests are available in different versions, suitable for virtually any situation or task. Next to different temperatures, we offer PCM packs in 2 different configurations: thin and flexible 8-cell packs, or thicker and longer-lasting 4-cell packs. Our PCM cooling vests will keep you cool for up to 4 hours. The effective cooling longevity depends on various factors: which type of PCM packs you are using, what you wear over your PCM vest, the ambient temperature, and how active you are. We recommend using a second set of PCM packs with your vest. You can stay cool for the entire day by simply wearing one set while the second is activating in your fridge or freezer. Activating PCM packs is simple. Place the packs in the fridge for an hour or in the freezer for 30 minutes. Be sure to place the packs in a flat position and not stacked on top of each other, as this will increase the activation time. It's also possible to activate PCM packs in cold water. The lower the water's temperature, the shorter it will take to reach maximum activation. The packs are activated when the PCM has turned completely solid. Activated PCM packs will stay cool and ready to use for up to 12 hours when activated in the freezer and stored in a small cooler. The PCM used in easy cool-down apparel is bio-based, non-toxic, and significantly less flammable compared to petrochemical PCM.
And even the research is done by installing the PCM at different locations in the refrigeration system. So here we can see the PCM that is placed in different locations. The first figure, you can see it is located after the compressor, before the condenser. Okay. Then the next figure, you can see it is placed after the condenser, before the evaporator. And the third one is fixed on after the evaporator and before the compressor. So in the first conditions, right, after compressor, right, the refrigerant will be of high temperature, right? So before getting into the condenser for cooling, if it is cooled through PCM, the effective cooling will be obtained. Okay. So likewise, this PCM is being used in the refrigeration system also. And here we can see the PCM is also used for thermal regulating textiles, used as a thermal regulating textiles. So according to the climatic environment, it will release the stored heat based on the body requirement, right? And the PCM will be laminated between the clothing material. So that can be used by the people, those who are working in adverse environmental conditions, especially in the industries. So, so here we can see, according to the human body requirement, the PCM will supply the energy to the body. Okay, so that will maintain basically the temperature. So that is the PCM based fabric material. So the next one, that is a method of integrating the PCM in the textiles, right? So here we can see a foam containing the PCM, right? And there are pressure rollers which sandwich the fabric. Okay, so for coating the microcapsules PCM onto the textile material, they are initially dispersed and wetted in the water solution. Dispersion embracing the thickener, the anti-fogging agent, dispersant, surfactant, and a polymer mixture, following which the coating is applied, right, on the textile substrate. So these are all the other innovative way of integrating the PCM in the textiles. So here we can see the methodology that is being adopted for integrating the PCM in the textiles. Basically, the spinning methodology is considered as one of the most widely employed techniques to integrate the PCM in the fabric, where different amounts of PCM along with the various liquid polymer or polymer solutions. Okay, so here we can see there is a drum collector. So this can be spun here, right? And the material will be supplied and it will be coated as we rotate this. So likewise, the coating is done on this, the polymer solution coating and other type of thing we can make it. Okay. So the spinning of fibers along with the PCM will enhance the protection of the capsulated PCM with the dual wall, where the first wall being the capsule and second wall being the fiber. Okay, so this is another way of making it. And the next another innovative way is use of the PCM for helmets. So often we could hear that people complained about the temperature rise in the helmet when they wear, especially during the sunny days. And people also will try to wear the helmet because of this high temperature. Some people also will get a headache. Okay. So in order to avoid the temperature, high rise in the temperature inside the helmet, okay, the macro-packed PCM is used, and it is provided over the comfort pad, right? It is between the shell, okay, between the shell and the comfort pad. So that PCM layer is fixed. So that will arrest the movement of more heat inside the space, helmet space. So by which the rider is comfortable in wearing the helmet. So these are all other innovative methodologies that is being adopted. The next one is incorporating the PCM material in buildings. So the selection of PCM depends upon the type of applications, like whether it is indoor space cooling or space heating, which needs low temperature thermal energy storage that is less than 50 degrees centigrade. So the use of PCM in buildings is ultimately will save the energy, and many researchers have done the extensive research on this. But however, there is no even a single PCM we can say that is available, which can be compatible for all building environmental conditions, right? So, but however, there are a lot of research work that has been going on for in enhancing the thermal properties of PCM in order to make them compatible for application of the thermal energy storage in buildings. However, the selection of PCM must be done according to the ambient environmental conditions, right? And the type of building envelope. So the encapsulation of the PCM will increase the heat transfer rate by increasing the surface area and in turn the thermal conductivity, right? And it also prevents the phase change material to come in direct contact with the building material and also the surrounding environment, by which the stability of the PCM also increases, right? So what is this macro encapsulation? This macro encapsulation of the PCM is the process of encapsulating the PCM in a shell material, right? Having a size of more than 5 mm. Okay, so that is the macro encapsulation. So the properties of the macro encapsulated PCM must be, it must maintain the indoor temperature under the thermal comfort range, and also it should be helpful in shifting the peak load to the off-peak hours. And basically, it must reduce the overall energy demand, which is required for space cooling. And also, it must reduce the indoor temperature swing. And most importantly, it must be chemically and physically stable. Okay, and it should not disturb or it should not create any harmful effects to the environment. Okay, so these are all some of the properties of the macro encapsulated PCM that has to be considered. It is a melting temperature, phase change enthalpy, right? The specific capacity, thermal conductivity, okay, whether it is economically viable, and it must be non-corrosive. Okay. So, for passive thermal energy systems, these PCMs are integrated into the constituent elements of the building envelope, like walls, floors, windows, roofs, ceilings, etc., without using mechanically assisted heating or cooling systems. So here the use of PCM is to increase the thermal energy of the building. Okay, so that is which is almost an old one. Now the concrete is considered the most used construction material, and many studies also proved that its energy capacity can further be increased by incorporating the PCM into the concrete mixtures. So here we can see the integration of the PCM in the building envelopes. So here we can see a brick with the hollow structures. So that hollow structure, in between the hollow structure, we can see another material that can be stored, which has lower thermal conductivity. And if we use these types of materials, one is here there is 3 layers. One is the layer with hollow, the other one is with the PCM integration, then the other one is hollow. Okay, so here the 3-layer protection is available. Okay, so these types of materials can be used for constructing the walls. So that will reduce the transfer of heat from the atmosphere to the indoor. Okay, which provides cooling, natural cooling. Then also macro PCM is also used for preparing the tiles, okay, wall tiles. So that also provides good cooling. Then use of the PCM with the steel balls. So here we can see the steel balls. Inside the steel balls, the PCM will be filled and it will be thoroughly fixed, right, without any gap. So when the temperature rises, okay, the solid PCM will be converted into liquid. Then, and if that atmospheric temperature reduces, then the PCM will liberate the heat through the metal and it will get solidified. In turn, it will releases the heat to the surrounding. So it will maintain the temperature in the desired condition. So in this way also, the PCM is being used. Now here we can see one video how the PCM pads are used to maintain the comfort in the buildings. So in the roof, as well as in the side walls, the PCM packs are fixed. Okay, so that will arrest or reduces the heat that is being transferred from the roof to the working environment. Okay, so these are all the other applications of PCMs in the buildings. Now, so far we discussed how the PCM is used in different sectors, right? Now, let us discuss about the characterization techniques of the PCM samples, right? So, one is the first work, what I'm going to discuss is about the preparation of nano encapsulated PCM samples. Okay, so here we can see the molten salt. So these are all the most commonly used PCM for medium and high temperature thermal energy storage systems. And these salts, they will exhibit excellent heat transfer properties and moderate volume change with temperature, and chemically stable even at high temperature conditions. Okay. However, there are some limitations like lower thermal conductivity, leakage at phase transition temperature. Okay. So these are all some of the things. Okay. Now, let us discuss here how to prepare a nano encapsulated PCM samples. So first one is, here we have to prepare a base salt. Okay. Then the next one is preparation of the nano encapsulated PCM sample. So how to prepare a base salt? So here the NaNO3 and KNO3 is taken around 60% of NaNO3 and 40% of KNO3 by weight is taken, and it will be mixed with 500 ml of distilled water. Okay, and this will be stirred in a magnetic stirrer for 1 hour at a temperature, atmospheric temperature, and that will be dried in an oven in a temperature of between 120 to 200 degrees centigrade for about 2 hours. Okay. Then it will be taken and filtered. It will be separated in a filter paper. So we got the base PCM. Now, using this base PCM, the nano enhanced PCM can be prepared. So that is this PCM, the required quantity will be mixed with the distilled water, and it will be stirred for 10 minutes at 800 RPM. Then the CPME and SPAN 80, these will be mixed for 3 hours. It has to be stirred for 3 hours with these mixtures. Then TEOS will be added, and once again it will be stirred for 1 hour. Then NH4OH will be added, and it will be washed with the distilled water and filtered. Okay. Then we will get a nano encapsulated PCM. Basically, the base PCM will be there, over which the coating is done. That is the nano encapsulation is done. So that is the one method. So likewise, another nano encapsulated PCM is also obtained similar to what we discussed over here. Okay. So in the first one, the SiO2 based PCM is prepared. In the second case, TiO2 PCM is prepared. So here we can see the surface structure of the base PCM salt in figure A, and for SiO2 in SiO2 based PCM in B, and TiO2 based PCM in figure C. So here we can see it's like a flake, right? Base PCM salt, whereas here it is spherical in shape, okay, which shows the formation of nano encapsulated PCM samples. And here we can find out the size of the SiO2 based PCM and TiO2 based PCM, which ranges between 200 to 500 microns. Okay. Then the next thing is that we need to determine the chemical stability of the samples. Okay. So the XRD analysis is done, and Fourier transform infrared, that analysis is done. Okay, so from the XRD peaks of the solar salt in NO3 KNO3 mixture, right? So here we can see the peaks are obtained at the black one is for pure PCM salt, and the red color is for NePCM, and the blue one is for NePCM 2. Okay, so almost it matches. Okay, there is no additional peaks from the XRD plot, and from the FTIR plot we can see the base salt consists of the symmetrical and asymmetrical at 1375 centimeter and 825 centimeter respectively. The bending vibration peaks of SiO can be obtained at the wavelengths of 1074 and 788 wave number respectively. Okay, so this shows the chemical stability. Next one is the differential scanning calorimetry, right? That heating rate at different heating rates, right? In the DAC we can obtain, and we can see how the variation is obtained, okay, for pure PCM salt and NePCM salt and NePCM C2 salt also, okay. And here the next figure shows the melting and solidification for PCM salt. So you can see the melting is quickly it is happening for SiO2. However, it is further the time for melting as well as the solidification is reduced for TiO2. Okay, so in this phase transition temperature, we can see the melting point for pure salt is at 228, and whereas for SiO2 it is 224 and further reduced at for TiO2. So this clearly shows that these materials can be used effectively for thermal energy storage. So the next one is we need to identify the specific heat capacity and the thermal conductivity, okay, and the mass loss also, because when we employ the PCM in the real-time environment, right, we should find out whether there is mass loss or not, right? So basically here, if you see the pure PCM, the heat capacity is almost 1.2 kilojoule per kilogram Kelvin, right? And it increases for NePCM 1, and further it enhances for NePCM 2, okay, that is TiO2 based salt. And similarly, the specific heat capacity is also increasing, and the thermal conductivity, if you see, it is higher for the TiO2 based PCM, and the thermal diffusivity is also higher, okay, compared to the SiO2 based PCM and pure PCM salt. And here we can see the thermogravimetric analysis plot. Okay, so there is a mass loss that occur around 150 degrees centigrade, right? Because we need to find out the TGA plot, because the thermal stability of the PCM is another critical parameter for designing the thermal energy storage system. Okay, so this TGA plot helps us in that. So the TGA plots of the base salt and NePCM we can see here, and they have shown almost identical weight loss. Okay, so there is a slight weight loss we can observe at around 130 degrees centigrade here. Okay, and that is due to evaporation of moisture in the sample. Then the degradation of nitrate particles begins after complete evaporation of PCM, and this degradation is further continued up to 760, 750 degree centigrade. So, based on this TGA result, the onset degradation temperature of pure NEPCM1 and NEPCM2 samples, we can say around 590 or 600 for NEPCM1, and somewhere here around 610 or 11, okay, for NEPCM2 samples. Okay. So we can easily understand that these NEPCM samples can safely operate at higher elevated temperatures, right? Even up to 600 or 650 degrees centigrade. Okay, so that gives a better thermal stability. So these are all the important findings when we use the PCM samples in the for the thermal energy storage systems. Okay. The next one is about the leakage test, right? We need to find out the leakage test also, because what happens when the temperature rises, right? This will melt and the leakage will happens. So there will be a mass loss. Okay, so we have to identify whether there is leakage or not. So basically, we can see the samples, the 3 base samples at the room temperature, that is at 300 degrees centigrade, and the elevated temperature we can see here. The NEPCM sample, it remains as it is, whereas there is small variation in the NEPCM SiO2 based. However, we can see a large variation in the leakage of the base PCM. Okay, so this helps us to understand and come to a conclusion that whether this PCM can be used or not. Okay, so especially when there is a solid liquid transition, okay, how this will perform, so that can be identified. So basically this type of experiments are conducted in open atmospheric condition. Okay, so
Sir, hello, sir.
yes, Mr. Ravi.
Sir, sorry to interrupt you, sir. Actually, sir, time is about to over, so we have
Okay,
very few
then
minutes.
so I think with this we can end up, and if there is any specific questions, right, the participants may post a message or they can send an email, okay, and I am ready to answer their queries. And if you have any other 1 or 2 questions, we can take up. Are you able to hear?
Yes, sir. So,
Okay.
sir, so I'll post your email ID in the chat box, sir.
Okay, okay, fine, that's
Any
fine.
queries is there, they will text you directly, sir.
Okay, okay, okay.
So, thank you, sir. I would like to express our sincere gratitude to our esteemed resource person for today's enlightening session on thermal energy storage technologies. Your detailed explanation of the various storage methods such as sensible heat, latent heat, and thermal chemical storage systems has given us valuable insights into the how thermal energy can be effectively captured, stored, and utilized. Your discussion on the practical application of these technologies in industries, buildings, and renewable energy integration has broadened our understanding of their importance in the achieving sustainable energy solution. The examples and research work you have shared added immense value and made the session highly engaging and informative. So we are truly grateful for your time and expertise and hope to benefit from more such thoughts-provoking sessions in the future. Thank you so much, sir.
Okay, thank you, the organizers, for providing me this opportunity to share my experiences and the research work that we are carrying out at NIT Tiruchirappalli. Once again, thank you.
Sir, please hold 2 minutes, sir. So we are going to take snapshots. So, dear participants, can you switch on your video so that we can take that snapshot for our references? Please kindly cooperate us.
Ravi, your voice is not audible.
Sir, please hold for 20 seconds, sir. We'll take in the capturing. Oh, okay, sir. Thank you so much, sir.
Thank you, sir.
Thank you, Ravi.
Sir.
Shall I end the session? You can end it now.
Okay, sir.
Yes, sir. Yes, sir. Sir, Dr. Subramanian, sir, you want to speak anything else?
Yeah, thank you so much, sir, for accepting our invitation and have a really this you have highlighted all the different types of energy storage system, sensible, latent heat, and thermochemical. I think really it is very informative to us, and I think even all the participants have been benefited from this conversation. Thank you so much, sir, once again for accepting our invitation.
Thank you, sir. Thank you.
Thank you, sir. Thank you so much, sir.
Dr. Ravi Kumar. So
Sir.
proceed to the next session. Dr. Sedakar already joined.
Yes, sir. Yes, sir.
Welcome, sir. Welcome, Sedakar.
Hello, thank you. Thank you, sir. I hope I am audible.
Fine, sir. It is audible.
Okay. Okay.